Okay, hi everybody, thanks for coming. The somewhat vague title of my talk is because I'm going to do, well, something possibly misguided, I hope not, and sort of try to give a little bouquet of sort of, in some sense, two shorter talks strung on a theme named in the title of Rational Points and Fundamental Groups. So really the sort of question that we want to have in mind throughout the talk is, what does the fundamental group of X, okay, so what's X? Some variety over a number field for today. And what's pi 1? Well, I have in mind the étal pi 1. I won't write this every time because this is always what I'm going to mean. This fundamental group developed by Grothendieck that studies the étal covers of this variety. And I want to know, what does pi 1 étal X tell us about the thing we're all here to discuss, the set of rational points on X over this global field? Well, I think in everything I'll say today, I'll have in mind that it's a number field. So conjecturally, the answer to this question is, maybe a lot. In the following sense, there's always, these are my notes, by the way, that I'm looking at on my phone, in case you're wondering why I'm looking at my phone. So exact, you always have an exact sequence connecting the geometric étal fundamental group, which is the étal fundamental group of this variety, base change to k bar, to the thing itself, the fundamental group, down to the Galois group of k, down to 1. And of course, one of the basic theorems that makes this go is that this is a group we can understand pretty well in the number field case. This is just isomorphic to the profinite completion of the usual pi 1, maybe I'll call it pi 1 top, of the complex points of X. And this construction, and I should say that this group is also known as the étal fundamental group of spec K. So because this construction is functorial, any point of the curve is going to give you a map on fundamental groups from spec K to X, which is just going to be a section of this map. So for every point P of xk, a section SP, and now, okay, nobody was pedantic enough to point out that I didn't put any base points on my fundamental group. Thank you for that. But because I didn't put any base points on my, now you're going to say it? Okay. Because I didn't put any base points on my fundamental group, I'd better say a section up to conjugacy. So this is like the lazy man's way of avoiding talking about base points. And so the so-called section conjecture posits that under some conditions, this is actually an isomorphism, that the rational points are actually in bijection with the sections of this map of topological groups, so a purely group theoretic object. This is an astonishingly audacious conjecture. We really have no idea how to prove it or whether it's true, but it's sort of part of the philosophy.
For certain varieties.
For certain varieties, exactly. So I sort of mumbled for certain varieties, so now let me say, what kind of varieties might this apply to? Well, for example, if X is P1, or a genus 0 curve in general, then this is a sphere. It's simply connected. So this is nothing. So OK, then obviously there's nothing to say. Right? So and that's a case where the fundamental group is not telling you very much about rational points. So let's just launch a tradition of vagueness that will persist throughout this talk. I guess up to conjugacy in here. So when x has big enough pi1, or some would say is non-abelian enough, some conjecture that xk is actually in bijection with sections. And then, you have to be careful if x is not proper. There's something one has to be careful about tangential base points. And but in particular, when x is a curve, which is going to be the case I'm going to talk about for the beginning of this talk. So when x is a curve, let's say the elliptic curve case is a little complicated. So let's say when genus x is bigger than 2, that's certainly bigger than or equal to 2. That's certainly a case that people who believe in this section conjecture would believe in this. Okay, so that's the kind of intro. And now I want to talk about, so sort of part 1. Fundamental groups and Chabauty. And all the work I want to report on here is joint with Daniel Hast, who's here. I will be happy to answer any technical questions that arise during this talk. So first, I'm sorry I'm going to be sort of reminding you briefly of a lot of things. So I already reminded you briefly of the Grothendieck fundamental group. Now I'll remind you briefly of what Chabauty does, which is the following remarkable theorem. So I'll state it like this. It's a sort of pre-Falting's method of controlling the rational points on a curve. So let's say if x, smooth proper curve, and I'm going to say it in a slightly more general form than it's sometimes stated, and x maps to an abelian variety, whose Mordell-Weil rank is strictly less than its dimension. So this is the so-called Shavuot condition. And I really want this to be, I don't want this to be like the constant map. So I want the induced map, and I want the A to be a quotient of the Jacobian. Then the number of rational points is finite. And even better than that, we can get really explicit control on the points by expressing them as the zeros of power series we can, at least in spirit, implicitly write down and calculate to arbitrary degree of precision. So maybe that's a little strong, but let's say indeed can be bounded in number, to give an example of the sort of goodness of information we have under this Shavuot condition. So this condition is much to be desired. And it's most frequently used when A just is the Jacobian. So often you'll hear people say, OK, I have like a genus 3 curve. Its Jacobian has rank less than 3. Then we're in the Shavuot case. And in some sense, by now, it's maybe it's too strong to say mechanical, but it's like tractable to actually, in many cases, to actually compute points. OK, this is an awesome theorem. The only problem is that this Shavuot condition, of course, does not always hold. Well, I don't know, of course, but it doesn't always hold. So, so I want to kind of discuss a sort of series of workarounds for this problem. Of course, we know by Faltings that curves of high genus have finitely many points, but the extra juice we get from Chabauty is very useful and is to be desired. So here's one. So not all x satisfy. Let me give this condition a name and call it, so C sort of refers to this whole cluster of good circumstance. So here's a trick that we do all the time in the study of rational points. Well, suppose I give myself some étal cover of x. Then we know that the rational points on x come from a finite and explicit list of twists of y. So so there exist twists y1 through ym, some finite set of y, such that if I take the union of the k points of y for I equals 1 to m, and then each one of those, of course, maps to the rational points of k, and the claim is that this is surjective. So this is what I mean when I say all the rational points on x come from a rational point of one of these twists x, y. Sorry, one of these twists of y. And the reason that this is potentially useful is that these, of course, an étale cover is typically going to have a lot bigger genus than the genus of x. And so even if x doesn't satisfy Chabauty, you have a chance that y might. And this is an approach that has actually worked in practice for certain curves. So is it possible there's always a choice of y such that y1 through ym all satisfy the Shavuot condition? When this works, some people call it étale Chabauty, and here we don't know. And I actually don't really know how to approach this question. So there's some cases where people have found covers that do it. I think a lot of people have thought about whether it's possible to sort of somehow rig up étale covers that satisfy Chabauty, and I think there's even some heuristic reason to believe that this probably should be true. I mean, after all, if you have some high genus curve over a number field, like out in space, we tend to think there's no reason for it to have high rank unless you gave it lots of points. So actually, this seems quite reasonable, except no one has any idea how to prove that this would always be true.
Is a twist a Galois conjugate?
Say again?
Is a twist a Galois conjugate?
Not exactly. So it's like, the way I always think of it is, okay, let's see the right way to say it. The question is, can I describe what these twists are a little more? I mean, one thing I can do is I can certainly pass. I didn't say an étale Galois extension, but I could certainly take the Galois closure and make it Galois. And then what I would be doing, then I would have a curve up here with an action of some finite group, and I would be twisting by Galois cohomology classes in H1 of Galois K on that finite group G, whatever it was. And then the reason that I would only have to look at finitely many is because I would have some guarantee that only finitely many primes, I would have some explicit list of primes that were allowed to ramify. So. Oh, that's a good example. Okay, so yeah, I mean, that's not an étale example, but it's a étale and GM. Étale and the GM, and then it's not finite. But yes, okay. I like that example. Okay, so as David points out, I could take GM to GM. So here it's not a finite list, but if I just take the map y to the d, then the twists and the sort of action is mu d. And so by Kummer theory, the cohomology I'm twisting by are like k star mod k star to the d. And then I'm really looking at the things mapping down. I mean, they're all isomorphic to GM, but it's mapping down, as David says, ay to the d. And then we're sort of making the sort of unsurprising statement that every rational point on GM is in the image of one of these maps for a some element of k star mod k star to the d. So that's sort of the sort of nature.
And it's finitely many if you're doing integral points.
That's a good point. Actually, that's right. So everything I'm going to say, just for so I don't go insane, is like proper curves and rational points. But like a lot of the story, feel free to integral along as you go, as David is doing. Okay. Okay. So let me now say a yet different direction in which people, I guess I could be using this thing, huh? All right, let me try it. So in another direction, because, I mean, you may have noticed I suddenly sort of stopped talking about fundamental groups, but really I still am. It's just that we might say that the Jacobian of x, I mean, the Jacobian is kind of a realization of the homology of X. And homology is just the abelianization of the fundamental group. So I would say it corresponds to the abelianized fundamental group of X, otherwise known as H1 of X, maybe with like z hat coefficients. And in fact, literally, maybe I should say over k bar. So this is some abelian group with an action of Galois on it. And like literally what it is the sum over L of the tape modules of the Jacobian of X. So when I say the Jacobian sort of corresponds to the no. Okay. So okay, I don't still have it up there, but like, I said at the beginning, maybe everything about rational points comes from this geometric fundamental group with its action of Galois upon it. So the abelianization of that, exactly what that's keeping track of, is the tape modules of the Jacobian. And so, any question one has about the abelianized fundamental group, one sort of naturally asks, is there some way to push this a little bit deeper into the fundamental group? And that's exactly what was accomplished by Min-Young Kim, I guess about 10 years ago now. So let me sort of say something about that. So Min-Young Kim explains how to extend Chabauty's ideas to, let's say, from pi 1 ab to pi 1. Well, not the whole pi 1, because let's face it, humankind is still not ready to understand the full fundamental group. But we just kind of we take very tiny baby steps out of the abelian case, and we say, let's mod out by L sub m of pi 1, where by this I just mean nth term of the lower central series. So in other words, we're going from abelian to nilpotent, which is kind of about as abelian you can be without actually being abelian. And so the wonderful thing that Min-Young does is he shows that there is a whole kind of a p-adic analytic story which does for this what the Jacobian does for the abelianized fundamental group and is good enough to allow you to make a Chabauty type argument. So what this is, I guess what I would say is, so Kim constructs, I'm going to be slightly loose by calling it a variety. It's sort of a p-adic analytic variety, U, which plays the role of J and shows that X of K is finite when it satisfies this sort of non-abelian Chabauty condition that this thing, which is not a real thing, really I mean sort of the rank of some Selmer object in Galois cohomology, is less than, okay, this is a literal thing. It actually is an analytic variety that has a dimension, so I don't have to put quotes around that. Okay, so this is the world's most vague rendition of what Min-Young did, but I think it's all in sort of half a talk. This is all I'm going to say about it. He brings that philosophy into this nilpotent context. And then the... Yeah, so maybe I'll write That's a great idea, actually. Because part of the game is now one might hope that by letting M be big enough, maybe even if the rank of J is very big, maybe that kind of comes out in the wash as we go deeper into the nilpotent filtration. And in many cases, that's exactly what happens. So let me tell you a theorem of John Coates and Kim, which uses this idea to show that if X over Q is such that Jacobian of X is a CM, abelian variety, then X over Q is finite. So maybe one way of saying it is that just as in the usual kind of theory of abelian varieties and summer groups that we do, Mordell-Weil ranks are controlled by summer groups, which are controlled by sort of some big piece of Galois cohomology. And for a general curve, I mean, the motives involved are some kind of crazy higher tensor products of symplectic representations, and we just don't know anything. We can make conjectures, but we don't know anything. So you help yourself. Of course, forcing the Jacobian to have CM makes the image of those Galois representations much more abelian, much more like class field theory, and so you give yourself a shot to actually prove something. And so in this case, they can push the philosophy all the way through and show that by making M large, they can make the Chabauty satisfied just under this condition and get finiteness for the number of points. Okay. But this is also, of course, not always true. So I'm sort of writing lots of workarounds and observing that in each case, they apply to sort of some classes of curves, but not others. So
sometimes there's a connection between the two over there, no?
Between?
I mean, do you mean to imply that there was a connection between them?
Which two things?
The two boards on the left, the top and the bottom.
I'm going to make a connection.
Yeah.
I'm going to sort of fiber product these two boards now. Okay.
I was thinking actually more about intersection.
Okay. All right, one of us is the product and one of us is the co-product, I think. I don't know. Okay, so I want to talk about this paper that Daniel and I wrote, which in some sense combines these strategies and extends the application to a broader class of curves. But the linchpin is this hilarious theorem of Bogomolov and Tschinkel that I love, and I always kind of wanted to use for something ever since I first saw it. So let me kind of tell you that theorem. And actually, we'll use it, and there's a version of it extended by Bjorn, which is what we'll use. So theorem Bogomolov and Tschinkel, and then I'll sort of and extended by Bjorn. So let x over k be. So Yuri and Fedor did the hyperelliptic case. And then Bjorn extended this to all superelliptic or even curves which are solvable covers of P1 curve. Then there exists a diagram x, y maps to x, and y also maps to x naught. What's x naught? It's this curve, y squared equals x to the 6th minus 1. So a genus 2 hyperelliptic curve, where this is a tall, and this is just some dominant map. So maybe this is old hat to everyone. I don't know. It's an old theorem by now. But I found this incredibly startling when I saw it, right? I mean, because the A-tall covers, there's like countably many of them. There's this very sparse set of curves of higher and higher genus. There's no sort of continuous motion, right, in the family of A-tall covers of X. And yet it's saying that you can find one that covers this specific hyperelliptic curve.
This is over K bar, right?
And this is over K bar, yeah. So that's actually important. So let me say that here. This map is over K bar.
What is K?
So actually, this part of Bogomolov-Tschinkel, I think, literally works for an arbitrary field. Is that right, Daniel? I don't think there's any number fieldness in this.
No, I thought it's just for like a number, like Q bar, I think.
Does this use Venkatesh?
Like I think.
It does.
I think for cardinality reasons, it would run into trouble over C. I don't remember a version for like C.
Okay, I'm gonna use it for number field, but I think this part of it doesn't use value, if I remember correctly. Okay. There are other things in the paper that do, but I think this does not. So
You're right.
okay. So let me kind of say this crazy. Okay, what order shall I say things in? Maybe first I'll say why this is useful and how we use this, because this actually sort of fits like a dovetail exactly into this issue that we've been discussing, because you'll notice that, of course, x naught, not only is it a nice Jacobian of a nice genus 2 curve, it's a genus 2 curve whose Jacobian has CM. So it's a genus 2 curve to which Coates-Kim applies. So what this tells us, OK, now I don't want to cover this because I want this, so I'm going to just erase this. Oh, actually, before I say anything about Chabauty, I will observe that in their paper, one thing that Bogomolov and Tschinkel mention is that, so thus, if an oracle told you that x naught of k is finite for all fields, for all number fields k, faultings for all hyperelliptic curves over all k would follow, essentially by the previous boards, because I would take my x, whatever it was, I would take the étale cover given to me by Bogomolov and Tschinkel. It would have a finite list of twists, but all of those would dominate x naught over some number field, and x naught has only finitely many points. The degree of this map would be whatever it is. That would give me a bound for the number of points on each twist of y, which would give me a bound for the points on x. So you can think of this as kind of like a faultings transport machine that brings faulting from like one fixed curve to like many others. I'll also say, of course, a big question you might ask when looking at this paper is what the hell is special about this curve? Yeah?
Is there also an effective version of this? Faulting tells you that this is true for this particular curve, but if you had an effective version of faultings for x naught, does this imply?
Yeah, because the degrees of this map you can pin down. If you sort of had the stamina to sort of sit down and trace it through, you could control. I don't know if you could, well, effective. You can control the numbers of things. You can control the heights, Daniel? Maybe. I think so. OK. Numbers, definitely. Let's say that. I mean,
These are very explicit. It's like 4 on one side and 16 on the other side, if I'm remembering right.
it's really a crazy theorem. OK. Anyway, so I ask, what's so special about this curve? And the answer is like maybe nothing. I mean, so that's what they can prove. But I mean, they ask, could it be that you can just put any curve over here? And this is true. So if you think that's ridiculous, try to disprove it. That would be interesting. What's x to the 6 minus 1? So I'm saying, I mean, they speculate there's no reason this couldn't be true with an arbitrary curve placed here, for all we know. Sure, why not?
I think they do it for x to the 5th minus 1 and x to the 8th as well. There's a few versions.
Oh, do they list some other curves? Oh, no, we use this one, so OK. OK, so let me just sort of say what we do in this paper. I mean, essentially, we can get the same conclusion almost from Coates and Kim, plus this theorem of Bogomolov-Tschinkel, and plus Bjorn's extension of it. I'll just say the wrinkle, and in some sense the main piece of work that we have to do, is that this curve, as you can see, is defined over Q. This one can be made to be defined over Q, but this map is definitely, as Mikhail helpfully pointed out, is definitely not over Q. And so we had to sort of slightly not so slightly in the end. We had to do something. But I mean, the argument of Coates and Kim can be made to work in that situation where the curves are not, where you have a curve which maps to a CM abelian variety, and the map is a geometric map. It's over some extension of Q, but the curve and the variety are over Q. You can show that the argument in Coates-Kim still gives the bound. So from slightly souped up to conclude that that x of Q is finite for any hyperelliptic curve x, or any curve that's a solvable cover of P1 by what Bjorn did. And again, for all we know, I said maybe this is true for every curve on this side. Also, maybe this is true for every curve on this side. So I say hyperelliptic or solvable because that's what they prove. But again, I challenge you, like, write down a curve that you can prove doesn't have an atal cover that geometrically dominates this particular curve. I have no idea how you would even start to prove that. But maybe. OK, so lots of questions here. So questions. Does a diagram like this exist for arbitrary x and x naught? Who knows? I think it's like a completely open landscape, and we don't know how to rule this out.
X always has genes.
Oh yeah, so certainly x should have big enough genus to have like a sort of handsome family of étale covers. So let's say that. Excellent. So 2 comments on this, and then I'm going to start the second talk. I'm exactly at half time, so that's good. So one comment is that in more recent work, I think both Daniel and Netan Dogra can actually show that the argument of Coates-Kim works for an arbitrary number field. So in that sense, that in a sense provides this oracle whose existence was gestured at by Bogomolov and Tschinkel. So in some sense, that's like another route that sort of gets around this kind of well, it's a better beef up of Coates and Kim than the beef up that we did in this. Now exists in pre-published separately by Hast and Dogra. And I can't resist just sort of finishing this part by saying the sort of philosophy that I learned from Yuri about sort of why they were thinking about stuff like this. I mean, you see, if I have a diagram like this and I look at what it says about fundamental groups, let's say about geometric fundamental groups, right? Because these maps are all over K bar. So, OK, ready? I have the geometric pi1 of x, and then I have the geometric pi1 of y. And this is a subgroup of finite index. And of course, since pi1 is functorial, this maps to pi1 of x naught over K bar. And this is typically, I think, going to be kind of like a surjection with some gigantic kernel. So you should think of this as like a quotient of this. I don't know if that's true in like every single case, but it's not so off to think of it as a quotient. So we're sort of saying, hey, x and x naught, their fundamental groups have something in common. Like this one has a finite index subgroup that has this one as a quotient. So I mean, I think this kind of crazy philosophy that Yuri talks a lot about is, what if like all curves actually have the same fundamental group? This is sort of some cosmetic difference like near the bottom that we see. But maybe actually, because after all, this you can think of as kind of a partial ordering on profinite groups with Galois action, right? Do I have a finite index subgroup that surjects onto U? And if so, then there's somehow some big chunk of our fundamental groups which exactly agrees, and maybe arithmetic information can be transferred from one curve to another thereby, which is exactly what happens here. And I'll just say that I think for all we know, it could be that every pair of curves of genus bigger than 2 kind of stand in this relation. I can't decide if that's like insane or a great idea to work on, but that's sort of the philosophy, and we see it instantiated in this case. So I'll sort of close this section with the question, do all curves have the same geometric fundamental group? And then you just have, these words are very vague, but you should sort of interpret them to make this possibly a true statement. OK. Yes, please, Ray.
Just a comment. This fails spectacularly in characteristic P.
Oh, tell.
That doesn't say anything about characteristic 0 because the difference is on the P part.
I see. So does this have to do with kind of like Akio's like stuff on like non-abelian and sort of seeing the invariance? Right. So I guess that's an excellent point. That somehow a curve with a supersingular Jacobian is going to look super different from a curve with an ordinary Jacobian as far as the p part of it, and that issue doesn't arise here. Okay, that's a really interesting point.
And actually, the conjecture there is that fundamental group characterizes the curve over up.
Ah, okay. But what if I said tame? Then would it not? Then would you crush everything? Okay. Right. Haha, see, I'm going to write tame here. Then I didn't say anything in characteristic 0, which is where I am, but then I'm evading Felipe's objection. Okay. Okay. So let me bring everything down. Should I? Okay. So I want to talk about a different way of sort of controlling points on curves, which is somewhat orthogonal to faulting somehow. And I want to start with recalling this really wonderful theorem of Heath-Brown. And really following on related work that was very influential of Bombieri and Pila, which says the following. And it says much more than this, but I'm going to sort of restrict to this one case. So let x, a plane curve of degree d. Then, if I look at the set of points of, and I think just for the sake of being careless, I'm going to write Q for everything here, but what I say here is all going to be sort of number field, general number field, whose height is less than b. So I'm counting points of height less than b, is less than c sub d b to the 2 over d plus epsilon. So if you haven't seen this theorem before, it's like worth stepping back and taking a look at it for a minute, because at first, if you don't think about it, it seems very unimpressive, because you're like, well, okay, a degree d plane curve is going to have genus about like on order like 1/2 d squared, so it's by default it's going to have finitely many points. Why are you telling me an asymptotic for the number of points it has of height at most b? And of course, the point of this theorem is that this constant is independent of what curve it is. That's what's quite amazing. So this is a uniform bound for points on a curve.
So is the curve supposed to be smooth or something?
No, nothing.
If you take a union of lines, then you get a problem.
Oh, yeah, OK. All right, so sorry. It doesn't need to be smooth, but it needs to be irreducible. Sorry. Thank you, Mikhail. OK.
Should that be a capital H?
A capital. Oh, yes, it should. OK. Wait, it's that height, not the log height. OK. And maybe I'll say, just because I worked hard on this for a long time and failed to do it, this epsilon has been removed by Miguel Walsh in a beautiful follow-up paper, so it's known to be. And in fact, I'll just say, since we're talking about non-smooth things, this is certainly sharp because we can just look at the curve like, so x to the d minus y to the d minus 1 z equals 0, and I'll leave it as an exercise to check that this kind of this rational curve, which is very singular at the origin, has on order b to the 2 over d points of height at most b. So you can't do any better than this. So this is this great kind of uniform in the curve bound on points in the curve. As I say, you see that you can't do any better. It's sharp because of a rational curve like this. And so I'm going to tell you about an old theorem that actually Venkatesh and I proved in this area. And then I'm going to tell you about a theorem that we proved and never wrote up because we don't have a good example. And then I'm going to throw myself on your mercy to give us a good example of an application of this theorem so that we have a reason to write it up. OK, that's my goal for the last 20 minutes. So this is a rational curve. And now I'll state a theorem of myself and Venkatesh from, I guess, 2005. If x is not rational, but the other conditions still apply, then we get a bound on order a uniform bound with a slightly smaller exponent minus delta of d. So you can beat it by a power. It's sort of a pain to actually explicitly get bounds for what this delta is. In the paper we show, we're able to show that for cubics, we get like 1 over 450. So it's not, I mean, you wouldn't notice the difference in like numerics or something, right? I mean, it's a pretty small difference, but we're just sort of trying to show that in principle that if your curve is not rational, then you can beat this power. And again, sort of what we're going to see is that the reason that you can do this is because once your curve is not rational, it has some fundamental group, and that's helping you. So let me give you a loose idea of the proof. Maybe I'll do it on the other board. Well, I can't do it now. I already sent that all the way up there. But let's all imagine that there's a number sign or an absolute value or something. But yeah, sorry. What? Oh, it's just for 3. Yeah, I'm just saying if delta was 900, that if d were 900, that delta would be like smaller than the smallest atom you could imagine. I don't know what it would be, but it would be bigger than 0 though. Okay. Oh, yeah, did I say delta bigger than 0? Okay, it's bigger than 0. Okay, so loose idea of the proof, which since Harald is here, is also very inspired by the work that Harald and Akshay did before this about sphere packing and points in Mordell-Weil groups, is that so since x is not rational, okay, for simplicity in this talk, I'm going to sort of assume x is smooth. If not, you can sort of normalize and play some games there. So x has a non-trivial Jacobian. We sort of choose some point and map x into j. And now we make the following kind of argument. Suppose x has many low height points, many, let's say capital N. That's always a big number. Okay. Well, then certainly the Jacobian has n low height points. But the Jacobian of x is, of course, some finitely generated group. And so we can sort of some rank R. So one thing we need to do is know that this rank is not too big. So there's a part where we say, well, you got to somehow bound the rank of the Jacobian in terms of the height of the curve, which you can do. I mean, the bound is somewhat crude, but you can do it. So which we bound. And j of k has at least. Now we're going to say, let me look at all these points and look at what they are mod m. Now, not mod m in the sense of reducing the coordinates mod m. No, I mean mod m in the sense of this group, in the sense of. So I'm going to say, so look at the map from j of k to j of k mod mj of k, which is otherwise known as z mod mz to the r. So great, this is a finite group whose order we just bounded because I bounded the rank. And if I have a lot of points in here of low height, then I better have a lot of points in some coset of this group. So So I'm going to completely not worry about torsion. That would be something that's absolutely, you're absolutely right. I mean, in this talk, I mean, obviously in the paper I mean, you know, in the end, this is analytic number theory, so you just sort of choose m between something and twice something and don't worry about constants and you can get rid of torsion. I mean, so yeah, there's going to be sort of, so as we sort of near the end, there'll be like lots of details that I don't say. I'm just, but to give the general idea. So there are at least n divided by m to the r low height points of j in some coset of mj of k. But then, of course, I can just subtract these from each other, right? I mean, and I still have control over how the height behaves under the addition on the variety. So whence n over m to the r points of low height, which are actually multiples of m, but then I can just divide these guys by m and get points of really low height. So so whence n to the m over r points of height 1 over m squared times whatever my height bound was. Okay, so whoever pointed out that I should have been writing capital H instead of little h, now I've totally screwed the pooch. I guess I should say b to the 1 over m squared probably, like, but I can't do it because I'm comparing with, I mean, partly this goes through, this is like literally exactly true for the canonical height in the abelian variety. Then that height divides by 1 over m squared, and then you use results saying that canonical height is not too far away from the Weil height that you're actually studying. So, and then this you sort of bound in some completely moronic way, that you sort of have the Jacobian and it's a projective variety and you can embed it in some way. I mean, you can make these heights like really small, so small that you can sort of trivially bound how many there can be. So this is nothing like a real description of the proof. It's like a cartoon from far away. Let me just make the following point about sort of what I see as the philosophy of this argument. So first of all, let me comment that the Heath-Brown philosophy is that, and then I'll just say sort of trivially show not too many of these. So saying there's not too many rational points which are in the same coset of mj of k, i.e. not too many pairs p1, p2 in x of k with p1 minus p2 a multiple of m in the Jacobian. I think this should be the takeaway, that somehow we're sort of saying this can't happen too often, and that's sort of what makes the proof go. And obviously this you can only do if you have a Jacobian. And that's what makes it work for non-rational curves. Okay, so Heath-Brown philosophy is that low height points repel each other in the topology on X of QP. So sometimes people call what Heath-Brown does, I think the thing Heath-Brown calls it this, the determinantal method, because to draw, again, like an incredibly reductive cartoon of what Heath-Brown's argument is doing, it's like saying, suppose you have like a ton of low height points in like a very small p-adic patch of your variety. Okay, ready? So here's your variety. It looks like this because it's a curve. Here's a very small p-adic patch of your variety. It looks like that because it's small. And then if we blow it up, that's what a small p-adic patch of your variety looks like, right? Like almost like a line. Everybody buying this picture? Okay. So if you have like a ton of points, they're all very close together p-adically, they're all kind of clustered together, then I draw them like this. And then the meat of Heath-Brown's argument is essentially to say, okay, let me sort of take the, well, first you sort of take some Veronese embedding to, so it's a little more complicated than that. But essentially you sort of take the simplex formed by all these things, and you're like, this is basically a line, and so that volume is like incredibly p-adically small, which means, so volume of simplex formed by these points is incredibly p-adically small, but it's also the determinant of some giant matrix that you make out of these coefficients which have a small height. So at the end of the day, the determinant is some integer which you have an upper bound on because the points have low height, but it's also like mega divisible by p, and then that could be a contradiction, right? If it's like, if you have something of height less than a billion that's divisible by p to the 10 billion, then that can't be, unless it's 0, and then you conclude from there. Okay, I can't believe how many really good number theorists I've like crushed their work to a ridiculous cartoon in this talk. But I did it to myself too, so I guess it's okay. Okay, so Heath-Brown philosophy, low height points repel each other in this, they're saying that the rational points kind of carry, they sit inside a topological space because they sit inside of XQP. Actually, in Heath-Brown, he also does it for X of R, by the way. I mean, I'm doing everything p-adically today, but you can, so they repel each other. And in some sense, the point of this paper I wrote with Akshay is that,
I think for me, the work Heath-Brown work p-adically, right?
say,
I mean,
I forgot what it,
but Heath-Brown works purely p-adically, I think.
oh, is that right?
I think so. At least everything I read by Heath.
Okay, you may, I mean,
It's technically easier sometimes than working over the real like computed p-dot.
I definitely find it easier to do it p-adically. I definitely find it easier to do it p-adically.
Yes, because the uniformity is easier to get sometimes.
Oh, so it's Bombieri-Pila who do it over R? Ah, I see. Okay. So maybe this is more a picture of Bombieri-Pila if you think it looks real. Okay. So, so the philosophy of this paper I wrote with Akshay is that there's another profinite topology on the rational points. Namely, if you remember what I told you at the very beginning, xk maps into, and for a curve you can actually show this map as injective, the space of sections of pi1 of xk bar down to, sorry, x1 of gal k up to conjugacy, which you can also write as h1 of Galois on the geometric fundamental group. And this is some piece of Galois cohomology whose coefficients are some profinite group. So it has a profinite topology too. And in fact, and when are things close to each other in topology? One example is if I abelianize this. So points of xk, sorry, let me actually write words. This provides another profinite topology on x of k when x has a sufficiently big fundamental group. So e.g., maybe it's easier to say that on the Jacobian, points P1 and P2 are close if P1 minus P2 is divisible by a large integer. So really we're sort of looking at the topology of xk going to this finally generated abelian group, tensored with ZP. That would be like the p-adic topology. And that's just a different way of saying which points are close to each other. And in some sense, the argument we make is that also in this topology, low height points repel each other, right? Because that's exactly what we did. We said it's hard for low height points to have a difference, which is like highly multiple by p or highly multiple by some integer. So somehow having both of these repulsion phenomena working together gets you a little bit of a better bound. In this topology too, low height points repel. So let me close by saying so let me say something we proved a little bit after this, but as I said, didn't really write up. So, fact, due to myself and Venkatesh, I don't know, maybe in like 2006 or something. Let x be, and now we're going to leave the realm of curves, okay? We're going to talk about higher dimensional varieties. Let x be a variety with large pi1 away from some subvariety z and x. Okay, so what does this mean? So this means, it certainly means that pi1 of x is infinite, but we don't want to do something screwy. So I mean, here's a way. I'm going to try to prove an upper bound for the number of rational points on such a thing. But the problem is, let's say we're thinking of like, what's a variety with like a nice big infinite pi1, like a torus or something. Okay, great. So there's a torus. But I could, if I wanted to be mean, just take a point on that torus and blow it up and get a p1, which would have lots of rational points. And I don't want to allow that. So what large pi1 away from z means is that if I take any subvariety that's not contained in z, the image of its pi1 is infinite in pi x. So I'm not allowed to have something like this where, well, it doesn't even have any pi1. So in principle, that certainly means that it had better have infinite pi1, and that pi1 has to survive to x. So you can't have like extra p1s spouting off. So don't worry, the definition is just you're not allowed to do this, basically. Okay, and let me just see the theorem statement in my notes. Let n, and of course a perfectly interesting case is where z is empty and there's just no subvariety whose fundamental group has finite image in x. Let n xz of b be the number of z integral points. So if z is empty, this just means rational points on x of k of height b. And the claim is going to be that, and this, by the way, is not going to be a uniform statement. This is just going to be a statement. So some constant, depending on epsilon and z and x and everything, times b to the epsilon. So in other words, what this says, let me sort of stand back and like look at this for a second. I mean, so first of all, it's funny because in Friedrich's talk, he made the distinction between kind of having an abelian pi1 and having a non-abelian pi1 because you were making the distinction between finite and infinite number of points. In this world, I don't know how to do that. We make a distinction between infinite and non-infinite. So instead of making the cutoff between genus 1 and 2, it's like making the cutoff between genus 0 and 1. And certainly, it's the case that genus 0 curves, right, have some power of b points of height at most b. And for genus 1 and up, it's like at most b to the epsilon. So what this is kind of saying is that it's not so much that phenomenon persists for higher dimensional varieties, that if you have an infinite pi1, then the number of points grows more slowly than any power of b. The problem is, it was actually kind of hard for us to come up with meaningful examples of the application of this theorem. So just to comment, I mean, one way you could have big pi 1 is if you have big h1, but then you have a big Albanese. So if you embed it in an abelian variety, then this statement is pretty clear, right? Because the abelian variety itself only has b to the epsilon points of height b. So you don't want that. You want to have and of course, if you just take, like, I mean, we talked a lot about, like points on hypersurfaces and stuff like that. Well, those are simply connected. Those are certainly not in this world. It's kind of hard to make varieties that have big fundamental group at all. Now you don't just want it to be big. You want it to be big but have no big abelian quotient. And the ones I can think of where I know that's true and can prove this condition are typically moduli spaces where for some other reason I know finiteness. So for instance, like, moduli of abelian varieties, moduli of K3 surfaces, stuff like that. I mean, these are big, hard theorems, but it is known already that those kinds of moduli spaces already are known to have finitely many integral points over like z brackets 1 over s or something like this. So, so I'll stop here and sort of solicit from anyone who wants to talk to me afterwards interesting varieties to which this might apply where you don't already know a finiteness statement for the number of rational or integral points. But whether or not there's an example, I still think it's a nice structural principle. Okay, so thank you guys so much. Yeah, Felipe.
That argument over there with the Jacobian, do you use non-first theorem?
No. We do not. Well, which you mean the thing about the sort of the thing that gives you log p? I mean, in some sense, I think there's so not anything hard about that. I mean, certainly that spirit of kind of sphere packing and points are repelling each other in Moore Leve sort of comes. That's a place or an earlier place that it appears for sure. Yeah, Dan.
So, what was I going to ask? I just forgot what I was. Let's
Okay. Oh, you had a question, Jack?
Yeah.
Okay.
In either Code Skim or what you and Daniel did, is there some analog of explicit p-adic analytic functions or things like that whose zeros give the rational points? Does that come into play somehow?
I mean, in principle, yes, but the way it works is really, in some sense, there's the stage where you show that sort of some rank is below some dimension, and that's what we do. And then that being the case, there exist those functions, but writing, I mean, it's sort of like it's a thing you know exists by dimension count, but writing them down in any specific case is like a very serious piece of work that we certainly did not do in any case. I mean, part of it is that in Coates Kim, I think you sort of need to sort of go up some unspecified distance in the nilpotent filtration. And as far as I know, so you guys know better than me and so does David actually, I don't think I know any case where people have explicitly written down the p-adic analytic stuff that vanishes on the points that goes farther than the first non-abelian step. Or am I wrong? Has somebody done an example where they actually go up to a 3 nilpotent group? I mean, there's people in the room who have actually done this amazing feat. Oh, is that right?
Yeah.
Okay. David's doing something else. Okay. Oh, I think you're okay. So yeah, P1 minus 3 points is always the place to start. Yeah, Dan.
So,
Was this the question you were originally going to ask, or did you think of a new one? Okay.
you were looking for varieties. So portions of totally symmetric spaces are automatically, this, or not interesting?
That seems like the kind of place. I mean, one would have to check, but that seems like the kind of place where if somehow something is homogeneous enough, that's where you have your best chance of sort of knowing a priori that there's sort of no kind of crazy subvarieties that are different and have small fundamental groups. So that seems. I mean, what's an example of one where we would be interested in the rational points? Okay. Or we don't already know, yeah. And those also sort of tend to have groups which are like arithmetic groups that don't have big abelian quotients. So that would be a place to look. Yeah.
How uniform is the dependency next?
I certainly don't know how to, I mean, so I'll point out that we certainly don't get a uniform b to the epsilon for curves. So I mean, making it, I think it's a great question, like, how uniform, if you're willing to sort of not have the right power of B, there's some kind of trade-off between how good of a power of B you get and how uniform you are. So in this generality, I don't think I know how to get anything non-trivial that's uniform, whereas in the case of curves, we're able to get sort of something slightly better than Heath-Brown uniformly, given the extra hypothesis of the big fundamental group. But, and of course, the ultimate, I mean, people used to speculate, and now I think like probably a majority believe that just on genus that there's like a uniform bound on the number of points of any genus G curve. I mean, that's certainly very far out of reach of things we know how to do now, but in terms of what's true, that means anything could be true, because it could be that just like all genus 5 curves have at most like 6,032 points. Over a fixed number field. Yeah. Yeah, Harald.
Yes, so actually I would like to understand better the connection between, well, I wanted to understand whether there are really two kinds of repulsion or three kinds of repulsion at play, because the paper with actually that you mentioned, we were also playing with this idea that you have repulsion in the sense of Combilicida, Heath-Brown, and so on, and you also have repulsion in the Mordell-Weil lattice. So there, that had already been found in different guides by Silverman, but in both kinds of repulsion, what we had was that, as you have said, if things are congruent to each other modulo P, then the repulsion becomes stronger. And the same is the case here. What I would like to get I would like to get your perspective on whether the second kind of repulsion here, namely the one that does not come from what you call the Heath-Brown philosophy, is the same or related to the kind of repulsion that we get on the Mordell-Weil lattice between integer points, or that you get in the Mordell-Weil lattice for genus 2 or higher, that was known already by Mumford.
Yeah, so that's a great question, and I'm embarrassed that at this moment I feel like I don't remember the guts of either your paper with Akshay or Mumford's paper like well enough to really answer it fully. I mean, one thing is that in your paper with Akshay, like there's a lot of work is done on Mordell-Weil tensor R, right? Do you consider that a different? Because that's also in our paper. I didn't talk about it here, but you can also, the sort of things that are really about sphere packing are sort of about things not being too close in Mordell-Weil tensor R, which is sort of in the same spirit, but not the same as Mordell-Weil tensor ZP. But I don't know if that's what you consider the third kind, or if it's yet a...
I think R and ZP in all of these are more or less equivalent, though often one is nicer than the other, technically. I don't think there's a big difference hiding in there.
Okay.
But there's what we do and what you did with action, what I did with action does feel different in some other ways, not completely. And not just in the theory versus R aspect. So I would actually like to understand it. I read your paper a long time ago, so I would like to understand the issue better.
Okay, cool. Okay.
Are there any other questions?
Yeah, Natan?
Do you think there's any hope of combining the two halves in the sense of, do you think there's any hope that any of these ideas could help to, when Chabauty's method applies, to bound the height of the reference, combining the information you have, or is that the wrong approach?
I never want to say something can't be done. I guess I don't see it. Like, I feel like these kinds of methods are, I think they'll never, I mean, to bound height, to get an effective bound, you really want to say, like, what's the biggest point? And I think these can kind of never do that. They kind of, they're, in some sense, like Shavuot, they're like bounding numbers of things, but I don't see how to, I mean, so I don't see it, but that doesn't mean it's, I mean, I applaud you trying to make it seem like I gave like one coherent talk instead of two separate talks.
I actually have a related question. So when it was discussed with the Untitled Chapter that also that's dominant map to this particular hyperelliptic curve, the question was raised of whether one could do anything about bounding the height using this construction.
Yeah.
It seemed actually like Bjorn had something to say about this, and I was curious as to whether you remember what it was.
Oh, I think, yeah, the doll effect.
Yes, so that's true, right? If your oracle were that I mentioned before were an effective oracle, which the current oracle that you and Daniel made is not, then I think that effectivity would traverse the Bogomolov Tschinkel diagram and give effectivity. So that's very true. So maybe that's a way to say it. At least now there's a mechanism that would kind of spread effectivity between different curves, except we don't really have it even for one curve. So.
Any more questions? Okay, we're done. All right.